Hi, today we're going to talk about groundwater, and we're going to start with a quick little brain pop.
Old Faithful was supposed to be over here someplace, but I can't seem to find it. Did you find Old Faithful? You know, the geyser. Dear Tim and Moby, I don't get what groundwater is. Can you explain it? From Joshua. Explaining's what we're here for, right, Moby? Okay, when water soaks into the earth, it becomes part of a system called groundwater. Soil is made of very tiny pieces of rock and organic debris. Weathered rock lies below the soil layer. Around the particles of soil and weathered rock are tiny spaces called pores, like the ones in a sponge. The soil is said to be permeable because water can seep through it and move through the groundwater system. Well, rocks may look totally solid, but some rocks, like sandstone, are also permeable with tiny pores all over. Groundwater moves through Earth's crust until it reaches a layer of impermeable rock. Materials like clay have really tiny pores, so water can't move through it easily, if at all. This makes it impermeable. When water hits the impermeable layer, it starts to well up and fill the pores of the permeable rock above. This area is known as the zone of saturation, and the top of that zone is called the water table. The surface level of a river or creek will show you the water table for a particular area. Wells go deep into the zone of saturation, so a pump can bring groundwater up to the surface. Water that can be pumped up to the surface often comes from a pooled area of rock called an aquifer. When the water table gets high enough to meet the Earth's surface, water flows out and makes a cold freshwater spring. Sometimes, groundwater is heated by hot rocks below Earth's surface and forms a hot spring. The park that we're in right now has both hot springs and geysers. A geyser is a hot spring that erupts every now and then, shooting hot water into the air. I'd like to show you a geyser, because they're really cool, but I can't seem to find the one we're looking for. Yeah, close call.
So this unit has been all about hydrology, which is the scientific study of the properties, distribution, and effects of water on the Earth's surface, in the soil and underlying rocks, and in the atmosphere. And we've so far been focusing on fresh water on the surface, and now we're focusing on water in the ground. Hydrogeologists study the distribution and movement of water below the Earth's surface, especially the distribution of groundwater, its flow, and then also groundwater quality. Here are some different pictures of hydrogeologists in action. You can see some of the types of things that they do on their job. This is a great job for those of you that really like to be outside and like to be doing things all the time and don't like to be confined to a desk. Although there is desk work involved in hydrology, most of it ends up being work that you do outside. Hydrologists need to understand what is under the surface, and they need to understand more about groundwater supplies here. And specifically, Michigan is underlain by 1,000 feet of something called bedrock, but most drinking water supplies are found in the uppermost few hundred feet. We know that glaciers have shaped Michigan's surface. We see some pictures here. On the left here we see glaciers advancing onto Michigan, and then here they are kind of at their furthest advance, and then as they retreated they had carved out these depressions, and then the leftover ice, the left behind ice, has formed the Great Lakes, and we see a lot of those features here in Michigan today. One reason that there's a lot of great ski hills in Michigan is because those are actually glacial till left over from those glaciers. Here is an idea of the thickness of the rock. Here on the left here we see the layers of the rock in the Grand Canyon that we're able to see, and this is the bedrock that we have under Michigan. So you see pretty deep in Michigan we have quite a few layers of bedrock down there. The bedrock in Michigan was deposited prior to the glaciation, and it was kind of in a bowl here, and so we can see that we have the Cambrian rocks, Ordovician, Silurian, and then Devonian and Mississippian, and they're kind of in this depression here, which we call the Michigan Basin. Hydrogeologists study rocks and their properties to understand how water moves underground. Some of the properties that they study are consolidated versus unconsolidated aquifer material, which I'll clarify in just a minute, the type and shape of the grains making up the aquifer, how the material affects water flow, and then also the potential environments of deposition from the past. So here are some examples of unconsolidated sediment. Unconsolidated means that the individual particles are not bound together. So we see some medium sand grains over here, there's some larger pebbles and gravel and coarse sand, and then we see our finest here would be the silt over here in the right-hand corner. When unconsolidated sediments become lithified, they're called consolidated. So once they become bound together or cemented together, then we call them rocks. Porosity is the amount of space between the grains of sediment and aquifer materials, and this can be between unconsolidated or consolidated materials. The amount of pore space is determined by a few different things, by the shape of the particles, the size of the particles, how the grains are sorted, and also what kinds of cements are holding the grains together. The greater the pore space or empty space in a rock, the more porous we say that the material is. It kind of makes sense that the roundness of the grain will affect how they fit together. So if we look at a picture here, these angular, kind of with sharp edges here, these are going to tend to fit together a little bit better than the rounded ones. So as the rounded ones come together, they're going to have a lot more space in between them. So the roundness does affect how the sediments fit together once they become compacted or lithified. Sorting is the measure of how they're distributed. Poorly sorted sediments have grains of many different sizes present, like we see right here at the top here. So these are poorly sorted because they're all mixed together. Well-sorted sediments, like we see right here, have grains of similar sizes altogether. And sometimes, like you see down here, you can have some larger grains floating around in a matrix of smaller grains. So in all of these pictures here, we're able to see different pores. So all of these materials here are porous. However, when the pores of a material are connected together, water and other fluids can flow through the material. The more fluids that can pass through the pores, the more permeable we say the material is. Rocks might be porous, but might not be considered permeable depending on how the pores are and if they're connected or not. So here we see two examples. This is well sorted, so again we see grains of a similar size, and so that's very, very porous. There are a lot of pore spaces there, and those pores are connected together, so water would be able to flow through there, so we say that's highly permeable. On the right-hand side here, we see poorly sorted material. So these smaller particles end up kind of taking up a lot of the space, so we don't have as many pore spaces, and so even though they're connected, we have lower permeability. And then on the bottom here, we see similar grain size, but on the left-hand side, it's uncemented, so water is able to travel from one pore to another, so we say it's highly permeable. On the right, even though there are quite a few pore spaces, they're cemented together, and so these pore spaces are isolated, and so we're not able to have water from this pore space travel to this one. So that is not very permeable at all. So let's just recap this idea of porosity versus permeability. So porosity is how much of a rock is open space, and permeability is the ability of a rock to allow fluids to pass through it. So you can have a very porous rock with a lot of pore spaces, but if water can't flow from one pore space to another, it would be impermeable. Water is stored in the pores of unconsolidated and consolidated material, and this is affected by gravity and pressure in groundwater. The water table level at any location shows us these effects. Pollution is a major threat to the relatively shallow nature of the water table and unconfined aquifers that we see in a lot of different parts of Michigan. So in this picture here, we see a few different vocab words when it comes to, or terminology when it comes to groundwater. The zone of aeration that we see up top here, these are where we have the pore spaces in the rock that are filled with air. And down here we see the zone of saturation, which is where the pores are filled with fluids. And then the water table is the boundary between those two zones, or the very top of that zone of saturation. We define an aquifer as an underground layer of water-bearing rock. And I like this picture a lot, but one thing I don't like about it is the fact that it shows the aquifer as blue, which might give people the misconception that this is actually a huge layer of water flowing, but actually an aquifer is a layer of rock that is able to hold water, kind of like a sponge. In Michigan, aquifers are typically unconsolidated because it's glacial sediment, so they're not cemented together, and we term these unconfined aquifers. They're easier to access, and they tend to be pretty shallow, not too far below the surface, but they are also then prone to pollution, which is not a good thing. Bedrock aquifers, however, are confined or are typically bounded by other rock units that don't allow as much water to pass through. So these might be harder to access, but they're less easily polluted. But if they're too deep in Michigan, then they might be briny, because remember, Michigan has quite a lot of salt deposits under the surface. Also, a well would be a structure like this one we see here that's used to draw water out of the aquifer. An artesian well is a well from which water flows upward under pressure. This type of well does not need a pump. It just naturally rises up to the surface, and the reason is because of the pressure here. Because the aquifer that it's drawing into is confined between layers of impermeable rock. So here we see sandstone is the aquifer here that the well goes into, and it has impermeable rock above it and below it, and so this causes quite a bit of pressure, so when we drill into that aquifer, water just naturally rises up from the pressure. So here's another good picture, and this shows a few different types of wells. So if we take a look here, we have an aquifer right here and an aquifer right here. Now this well over here drills into that first aquifer. It is not confined, it's an unconfined aquifer, so in order to get water out of that well, you would have to pump it out. Now this aquifer here is confined. It has a layer, an impermeable layer above and below it. So this well right here, if we draw into it, water is going to naturally rise up here. This one, because it's a little bit deeper even, and you can see its opening here is at this level right here. So this one actually is going to, the water is going to continuously flow out of it. Here we see some really nice maps of Michigan's geology. Here on the right-hand side, these different colors are showing us different bedrock aquifers. So you can see we do have some bedrock aquifers in Michigan, and then the other areas do not bear water there. The depositional environment can affect aquifers themselves. This word deltaic deposits are deposits that are deposited at a delta or at the mouth of a river entering the ocean. And these typically tend to be sandy or muddy and have lots of plants there. And so when they get buried very deeply and compacted and form into rock, they typically turn into sandstone or mudstone or siltstone. And sandstones here can be a very good source, very good water-bearing rocks. The mudstones and siltstones, however, might be barriers to water flow because the particles are so small there's not a lot of pore space. Organic material that gets trapped in the rock from swampy areas might cause poor water quality because they can tend to release gases, and also the vegetation decaying can release a lot of chemicals into the water there. Humans can contaminate water in quite a few different ways. We see here a deep injection well, so this one goes deep into the sandstone layer here. Here's a shallower well into this alluvium deposit here, so both of these are wells into aquifers here. What we have here are a few different examples of some contamination. We have a disposal pond here where this business here is disposing of toxic materials, and we can see that the water flow here in this aquifer is heading towards the river. And so all of those disposals are going to head not only towards the river, but they're also going to contaminate some water supplies there. And so we have buried waste and so on. So all of these things tend to cause contamination. We also have some deep fractures here. This might possibly be from the damage from this well, and these fractures are probably from this river. And so pollution can also travel through those different fractures. This is an example of something that we don't see a lot of here because we're not close to the ocean, but in people that have wells close to the ocean, what ends up happening is, even though it might be in a freshwater aquifer, if they're too close, salt water can fill in those pore spaces and can be drawn into that well. So this is called saltwater encroachment, and this is typically happens in deep bedrock aquifers. But remember that Michigan also does, even though we're not near an ocean, we do have those salt deposits from the ocean from Michigan's past, and so some aquifers do tend to be briny from that past ocean environment in Michigan. So that's it for our video on groundwater. Thanks for watching.